So today we are discussing geometric probability. This is going to be helpful for your summative assessment where you're designing games. You may or may not have to determine probability in 2 dimensions using area. You may have to find probability using angle measures in sectors of circles, using length and time. So we're going to be focusing on that today. So all of these objectives. So we're going to leave investigating experimental and theoretical probability for tomorrow. So if you're gone today, primarily you want to focus on this lecture, and then tomorrow is an activity on experimental and theoretical probability. So just a couple reminders for us on this slide. It tells us what probability is. We already know that it's a number between 0 and 1. You know that if you get a number over 1 that you did something wrong. Geometric probability, it's the same concept, except it's going to be involving geometric shapes, geometric measures such as length and area. You will have to know basic area formulas, which at this point in grade 9, you already know how to calculate the area of simple shapes, and you already know how to calculate the area of shapes that are combined, right? You just add all the areas up. So to find geometric probability, to find regular probability, you take the ratio of the number of desired outcomes to the total number of possible outcomes. Again, that's frequency over total. So we've got our understanding of probability now transferred to geometry here on the bottom. If we're talking about length of segments, which we will talk about in a moment, the probability that a certain event will occur with a given length, let's say that it's going to be of a certain length, its desired length over total length of the segment. For area, it's desired area over total area. This is going to make more sense when we look at an actual problem in the context of that problem. But just keep in mind, it's the same type of thing. We're just adding a geometric element to it. Any questions? Darts. So darts is a game in which the darts are thrown at a circular target. The target or dartboard consists of different areas that are worth a different amount of points. The player that scores the most points wins the game. We've all played darts and we have a dartboard in the classroom. So we can determine the probability that you will land in a certain area within your dartboard by just doing some simple calculations, okay? So that's if we know the dimensions, right? If we know the dimensions of the target board and the dartboard itself. So notice here they give you dimensions. They say find the probability that a dart lands in the red region. Well, the probability using geometric figures is the desired area over the total area, right? So our desired area is the red area. So that's a circle. So we need to remember that with a circle, the area is pi r squared. And we've all seen that before in like 6th grade, maybe earlier. Pi r squared. So as long as you have your radius, if you don't have it, you have to measure it. Use your geometric tools to measure it. Pi r squared. Find that red circle area and put that over, make the ratio over the square area, the area that encompasses the dartboard. So that would be 16 times 16. You do 12.57 inches squared over 256 inches squared. Remember, squared, because we're dealing with area, you get 0.049. So it turns out that you have a 4.9% chance that you will hit within that red region of your dartboard. Okay, so if you wanted to use the classroom dartboard for your summative assessment, it's an expectation that you're actually finding that radius yourself. Okay. Questions? Excellent. Not that hard. So in contrast, if we wanted to find the area of the yellow region, it's the same thing, except you have, if I zoom in here, you have a longer radius. In fact, you have an additional 3 inches. So let's see what they did here. So the yellow ring area, notice they're adding a step. The yellow ring is just a ring, right? So what did they do? They took the yellow circle area minus the red circle area, and what you're left with is the yellow ring. Does that make sense? because of course you just want that sliver. I hate that word, sliver. So they did that. They found the area of the yellow circle, area of the red circle, found the difference. 15.73 is the area of that yellow sliver. You take that divided by the total area, which has not changed, still 16 inches by 16 inches. So still 256. 15.73 inches squared divided by 256 inches squared, and you get 0.061. So you have a 6.1% chance that you're going to land in the yellow region. Melanie, put away your phone. Question? No? Pretty simple, yeah? Just common sense with the subtraction part. This is where we have to apply some of what we learned this year. Okay, so this is a little bit different. It says find the probability that a chosen point, or that a point chosen at random, lies in the equilateral triangle given a semicircle with radius 8 feet and an equilateral triangle with side length of 6 feet. So the way we find the probability has not changed. It's still the triangle's area over the semicircle area. So it's still the triangle's area because that's the desired region over the semicircle area because that encompasses the whole thing. Now, we have to find the triangle's area. Now, because it's equilateral, we're used to 1/2 base times height, but that only works for what kind of triangles? Right triangles. There's another formula that we can use to find the area of any given triangle, which we'll talk more about next year. But for now, we're going to work within that stipulation, the 1/2 base times height. Now, there is something that I'm going to introduce to you here called an apothem. So it says the triangle's area. So for a regular polygon, it's 1/2 of the apothem times the perimeter. So I'm going to write this in words, and then I'll tell you what an apothem is. It's not a possum with a lisp, but it's something in geometry, okay, apothem. So 1/2 times apothem times perimeter. Now your apothem can be applied to any regular polygon. What's a regular polygon? Melanie, what's a regular polygon? What's that? What? Put it in words. Melanie. It's a shape. What kind of shape? Any shape? Nope. No. A polygon. Not a pentagon, not a hexagon, a polygon, yes. A polygon. It's an enclosed shape. An enclosed shape with any given number of sides. Now, when you narrow the side lengths down, you have hexagon, heptagon, pentagon, octagon. But a polygon is just an enclosed shape. Yes, it has to have straight side lengths. That's why we don't classify a circle as a polygon, right? And we went in that whole argument about is a circle an infinite gon or whatever. But under our understanding in mathematics so far, a polygon is an enclosed shape that has sides such that those sides are straight lines or segments, we should say. Okay? So, for any regular polygon, this will work for the area. 1/2 times the apothem times the perimeter. So what's an apothem? The apothem is the segment that starts at the center of whatever your regular polygon is. In this case, it's an equilateral triangle. And from the center to one of the sides, it will split the side in half and form a right angle. Okay, so it splits the side in half and it forms a right angle. So I'm going to define that for you, and I'd like you to put that in your notes or write that somewhere. So here is the apothem. So from the center of your polygon, to the midpoint. And it's also perpendicular to the side. So it's that segment from the center of your polygon to the midpoint, and it's also perpendicular to the side. That's what we call an apothem. It helps us determine the area of our triangle. And I'll move this up so you can see it. Just give me a moment here. All right, so to find the area of our triangle, our equilateral triangle, we're going to make the correct assumption that it is a polygon, a regular polygon with 3 sides. So we apply this formula that says to find the area of that regular polygon, we do 1/2 times the apothem times the perimeter. The perimeter of our triangle we can just find by adding up all the sides. Yes?
What does it mean by from the center?
From the center of from the center, so it's the segment that extends from the center of your polygon to one of the sides. It can go to any of the sides, right? And when this apothem goes from the center of your regular polygon to the side, it splits the side in half. So this is 3 and this is 3. And it's also perpendicular. So now, if we do this, we have right triangles, right? In fact, we have a special right triangle because we know that equilateral triangles, what are the measurements of all the degrees in an equilateral triangle, each of the individual angles? 60. And what'll happen here is this will actually get bisected. So we end up with a special right triangle, a 30, 60, 90 triangle, which is good review for us anyways because we'll have a final where you're going to be asked to find the side lengths of special right triangles. You following so far? Okay. So we did that so we can have a right triangle that we know how to work with. There are 2 ways that you can do this. If you remember the ratio of the side lengths of your special right triangles, the lengths of your side lengths for your special right triangles, then you can use special right triangles to solve this question. So I'm going to do it both ways. If you don't remember, you can just use trigonometry. So here is our triangle. Okay. It forms that right angle. We know that that's 3 and that that's 3. We know that that's 30 degrees, which means that this is 60 degrees, right? Because this angle is bisected, and in an equilateral triangle, all the angles are 60 degrees. Are you following? Okay, so let me just write this out a little bit bigger. This is 30 degrees, this is 90 degrees, and this is 60 degrees. In our 30, 60, 90 degree triangle, do you remember the side lengths in terms of x? So close, yeah. So 30 is x, right? X root 2. Oh, sorry, x root 3. X root 3. Yeah, x root 3 and 2x. Yeah. So looking at this, we have the one across from the 60, right? So to solve it this way, you set 3 equal to x square root 3. Remember that? To find the length of x. Because we need our base and height. Yeah. So when you solve this, 3 equals x root 3. You divide by root 3. 3 over root 3 equals x. I don't like my radicals in my denominator. This is good review. So how do I get rid of my radical in the denominator? by what? Yeah, root 3 over 3. So, sorry, root 3 over root 3. So this is 3 root 3 over 3. That's equal to x. So x is equal to square root 3. Meaning that this side is equal to square root 3. Does that make sense? So now you've got a base and a height for a triangle, right? And you can find the area of the triangle. So that's what you did. So they did 1/2 times the base times the height. Actually, you don't even need that. Sorry. The formula just says the area is 1/2 times the apothem times the perimeter, right? So that's what they did here. They found the perimeter of the triangle, which this is 18 because each of the sides is 6 units. Does that make sense? The apothem we just found was square root of 3, which is 1.73. So the area is 1/2 times 1.73 times 18. Does that make sense?
Wait, where do you use the perimeter?
So if you're using, if instead of using 1/2 base times height, you use this formula. This is an alternative formula. This is an alternative formula to your triangle formula area. Does that make sense? It's alternative. So instead of using 1/2 base times height, we're using 1/2 AP. 1/2 apothem times perimeter. So we have to find the apothem, which we found here, using special right triangles that Eric helped me out with. And then we need to find the perimeter of the triangle. And the perimeter is 6 plus 6 plus 6. Does that make sense?
Yeah.
So 1/2, 1.73 times 18 is 15.57. Does that make sense? Yeah. Did you take 1.73 times 18 divided by 2?
Wait, so x is square root of?
Yeah. So if you take the square root of 3, you should get 1.73.
Why did I get 15.58 on the
Could just run.
Well, how did you round square root of 3?
calculator? I just put square root of 3 times.
Oh, well, that yours is more accurate then. If you're just using 1.73, chances are that this is less accurate. In fact, let's make this a more accurate answer. We need to change this equal sign to an approximate sign, right? Okay.
When the calculator just tells you square root of 3 is square root of 3.
Yeah. Questions? Other questions? These are all good. Now let's say you forget your special right triangles. You can always use trig. Right? You can use SOHCAHTOA. So if you use SOHCAHTOA, then you have opposite over adjacent. You're trying to find the opposite, you have the adjacent. Right? So you do tangent of 60 equals 3 over x. And you get the apothem. And you apply it's the same formula. So does everyone feel comfortable with the 1/2 apothem times perimeter formula? So go back to this whenever you're doing the homework problems, which I'll give you today and tomorrow to do, and I will walk around and help you. Go back to this example and see how it's done. Now, to find the probability that the point lies in the triangle, I have to take that triangle's area and divide it by what? The semicircle. Well, how do I find the area of a circle? No, that's circumference. 2 pi r circumference. Pi r squared. Yeah. Yeah, take pi r squared divided by 2, right? So that's what they did here. They have the r, which they give you, is 8. You take pi r squared divided by 2, you get 100.5. So finally, you take that 15.57 divided by the 100.5, and you end up with 0.155, which is 15.5%. So you have a 15.5% chance that if you were to throw something in an area that's shaped like a semicircle with a triangle inside of it, that you will land in that area. So if you are interested in doing geometric probability, like I said, for your summative, and you want to explore these shapes and do some kind of complex dartboard game, you can. And if you do a complex dartboard game, you have to show these calculations so that I can see, okay, what is the probability that the person lands in the area that you want them to land in, you know? Questions? No? Now, this doesn't mean everybody should be doing geometric probability. It's just that I know some of you want to. To find the geometric probability of length, so it says find the probability that a point chosen at random lies on a certain segment, TU. All it is the length of TU over the length of RS. Now, because it's a straight segment, you can simply count, but also remember that length is just the absolute value of the difference. So if you were to just to verify, the length of TU, that would be the absolute value of the difference between U and T. Yeah?
So length is the space between them.
Is a space between them. So you can either count or the calculation is this. Now, it's important to understand conceptually what this means. This means that anytime you have a straight line, not a diagonal line, so a horizontal line or a vertical line, and for some reason it's difficult to count exact units, you can apply this formula, which is called a ruler postulate. It's not really a formula, it's a postulate that says that if I want to find the distance in a straight line, it's just the absolute value of the difference. And we've talked about that before, so you're just applying that again. You take the length of TU over the length of the total, which again is 10 minus 0, the absolute value of that, or 0 minus 10, either one. You get 2 over 10, which is 1/5. So you got a 20% chance that you will choose a point on the segment TU.
If it's a diagonal line, you just use the distance.
Yes, if it's a so Johnson asked you a great question. If it's a diagonal line, you'd have to use the distance formula, right? If it's a straight line, it's just subtraction. Now this is good. Maybe you want to develop a game, you know, those games where, you know, you have ducks in a row or something. Think about using this. So all of these are real life applications that you can use when you make your games. Questions? No. All right. Here's another example. Find the probability that a point chosen at random lies on LM. You would do the same thing. You can either physically count those units. You can take the absolute value of the difference between 35 and 20 and put that over the length of the total, 70 minus 20, which is 50, and you get 30%. We're going to turn it up a notch. Don't worry, it gets harder. Let's look at time. So this says time can be represented on a number line because it occurs in one dimension. While watching television, you see a commercial for car insurance. If the commercial replays at a random time in each 3-hour interval, what is the probability that you will see the commercial during a 45-minute television show? Right? So it's the same idea, desired area over, or desired length over total length, right? We know that within 3 hours, you can see this commercial, right? It replays each 3-hour interval, in fact. Within one of those 3-hour intervals, you're going to be watching a 35-minute television show. So the way they laid this out was, okay, let's look at a span of 3 hours. Okay, if I'm talking about a 45-minute television show, how I need to get them in the same units, right? So how can I express 45 minutes in terms of hours? Right, but we have this horizontal line that goes from 0 to 3, and that 3 represents 3 hours. So how do I find how many hours that I'm dealing with if it's all in the same unit? Okay, someone other than Johnson. How do you convert minutes to hours?
There's 60 minutes in an hour.
Okay, there is 60 minutes in an hour, so how do you use that conversion rate to get your minutes into hours?
Divide by 60.
Mm-hmm. Yeah, because I'm just curious. I want to know here. So go ahead and do that. Take your 45 minutes, divide it by 60. 0.75. So it turns out that for a 45-minute television show, that's 0.75 hours. Right? Now, you can simply count. But let's say that we wanted to verify this algebraically. Okay? How could we do that? Well, there are 3 hours, right? How many total units on that line represents 3 hours? How many total units goes from here to here? 12, right? 12. 0.75 over x. If we want to verify how many units it is algebraically, of course we can count. Cross multiply and solve for x, what do you get? Solve. 12 times 0.75 divided by 3. 3? Yep. So this is 3 units, right? Which we can verify by counting, and we can set up a simple proportion. So you could simply take 3 over 12, right? 3 over 12 is 1/4, which is 25%. Okay, now they give you another way that you can do it. You could look at this unit rate, how many minutes represent 1 unit. Just for fun, how do you determine how many minutes represent 1 unit? How did they come up with 15 minutes is 1 unit?
They divided 1 hour.
Okay, so you get 0.25, and then you take 0.25 times 60, and you get 15 minutes, right? Questions? No? Straightforward? Last minute questions for the people that are watching. No. Okay, so let's go here. This is easy. If you have a circle and you have a sector, what's a sector? A piece of that circle, right? Like a pizza and a pizza pie, a pizza slice. On circles, you can use angle measures to find geometric probability. The ratio of a sector's central angle to the entire, so what's a central angle? The angle in the center, right? Again, final exam, you're gonna have circles on it. The ratio of a sector's central angle to the entire circle is 360, we already know that. It's the same as the ratio of the area of the sector to the area of the entire circle, so you just find the measure of the angle over 360. Okay, easy, right? So, here's an example. The probability that in a spinner, now this time we are given angle measures, right? So this is the geometry part of it. You just take that sector, the degree measurement of the angle over, 360. Notice you're still going to apply those multiplication and addition rules. The probability that you land on brown or green, it's just the addition of those 2 sectors over 360, right? The probability that you land not on blue, is there a blue there? Oh, okay. Yeah, the probability that you land not on blue, you take 1 minus that, the probability that you do, right? Or 100%. Questions?
Is this what the grade 10 from last year did on your spinner? Around the wheel of fortune?
I don't know what they did specifically, but they did something with a spinner. So you could potentially combine some of the things that you practiced with yesterday on that worksheet. That's why it was very important that you did that worksheet. Because if you understand the probability in that worksheet and you understand those scenarios, then you're going to be able to do the mathematics correctly on your summative assessment. If you understand the concepts that are needed to be applied on the spinner problems there, and you're able to combine it with something like this, then you're able to turn in a good assessment. Because you show me not only that you're able to analyze a spinner problem, you're able to analyze it in many different ways. For example, with the angle measurements as opposed to just saying the probability of landing in a certain area is, 3 out of 5 or whatever.
Are
Yeah.
we having groups on this summative?
What groups?
Yeah.
No.
This is the individual.
Yeah, I think it's individual. I'll have to double check to see how Miss Chi did it last year. But I'm going to end this recording, so if you are watching this, you need to do the homework on geometric probability. It's under the homework tab. So open that up. If you open it up and it doesn't have geometry in it, you're on the wrong assignment. Okay.